Hello everybody, in this video we will explore the microstructural and rheological phenomena that occurs in fat-reduced yogurt due to processing. In short, yogurt processing involves the standardization of milk to get the right composition of fat and milk solids, which plays an important role in yogurt structure. Then the milk is pasteurized and homogenized to get rid of pathogens and get uniform fat droplets. The product is then inoculated with starter culture and fermented, followed by chilling. The creamy lusciousness is then packaged and shipped off to be enjoyed. Let us understand the microstructural changes that occurs in yogurt due to processing using simple kitchen experiments. Experiment 1. Effect of heating on complex hydrocolloid networks. In order to demonstrate microstructural changes that occur during pasteurization and mixing process, we prepare 5% gelatin solution, 10% starch solution, milk with gelatin at 5% concentration, and yogurt sample with 5% gelatin and 10% starch concentration with 100 ml water. The 5% gelatin solution, 10% starch solution, and gelatin with milk solution serve as the controls. All four solutions are subjected to heating in a water bath to facilitate gelatinization. As a result, we can see that there is an increase in viscosity in all the samples after heating.
Heating treatment in yogurt product is used to denature the raw proteins. This allows the proteins to form a more stable gel, which prevents separation of water during storage. The cross-linking capacity of denatured whey proteins play a key role in yogurt structure after heating. It contributes to an increasing in the degree of bridging between protein particles.
Experiment 2. Effect of pH on casein in milk. In this experiment, we demonstrate the fermentation process. As starter culture wasn't available, 38% lactic acid is used at 1% to the resultant yogurt sample from experiment 1 at approximately 40 degrees Celsius. As a result, we can see that the casein has precipitated from the yogurt sample and aggregated to form clumps.
During acidification, casein and whey protein aggregate, increasing the consistency of yogurt. The quantity of minerals in yogurt remain the same as in milk. The only change is that, due to the pH lowering, these minerals are ionized rather than colloidal form. The concentration of lactic acid increases during the fermentation. The pH decreases. Therefore, the carboxyl groups dissociate. Serine phosphate is ionized, which raises the negative charge between the casein micelles. However, the presence of calcium phosphate neutralizes this negative charge, keeping electrostatic repulsion down to a level where attractive forces between the protein molecules are dominant. Due to these attractive forces, the casein micelles aggregate and eventually coagulate into a network of small chains. This is responsible for the increase of viscosity and formation of the yogurt coagulum.
Experiment 3. Effect of cooling on complex hydrocolloid networks. In this experiment, we demonstrate chilling process of yogurt processing. Samples of 5% gelatin solution, 10% starch solution, milk with gelatin at 5% solution, and fermented yogurt samples are chilled at 4 degrees Celsius for 4 hours. As a result, we can see that the gelatin control and milk control have thickened to form a compact gel. Starch control has increased in viscosity, however, yogurt control has the least viscosity.
After the pH reaches 4.7 to 4.3, the yogurt is cooled to around 5 degrees. This prohibits the growth and metabolic reaction of the starter culture and prevents the increase in acidity. Cooling of yogurt can be in one or two phases. One phase cooling involves the rapid decrease of the coagulum temperature to less than 10 degrees, where the fermentation process is inhibited, leading to yogurt with low viscosity. Two-phase cooling is initiated by rapid decreasing the temperature to less than 20 degrees, and then gradually reaching the storage temperature of 5 degrees, leading to yogurt with an increased viscosity and limited syneresis.
Experiment 4. Effect of shear stress on yogurt gels. Let us assume that our homemade yogurt turned into this. In this experiment, we replicate the shelf life and use of yogurt in order to study syneresis. The yogurt is stirred with a spoon and left for 3 days in the refrigerator. We can see that the yogurt has leached out, whey, and is clumpy. Yogurt is a non-Newtonian thixotropic fluid. As seen on the graph, the viscosity of the yogurt gel decreases when shear increases, and the breakdown of the structure is not totally reversible when the application of shear stops. Yogurt exhibits syneresis, which is the expulsion of the whey serum from the yogurt network by the shrinkage or contraction of the gel due to external forces, and is related to instability of the gel network due to the increasing rearrangements of the gel. It is found that the excessive shearing in the yogurt results in considerable loss of structure and may result in a weak body, as shown in the figure below, decreasing of the viscosity in every formula when different shear rate was applied. The expopolysaccharides in the serum phase increase product viscosity and water holding capacity. When a high shear is applied, the expopolysaccharides are broken up, large deformations occur to casein gels, and the system becomes nearly Newtonian fluid. Thanks for watching, everyone. We'll see you next week with techniques used to assess the microstructural quality of this delicious goodness.